The challenge in modern statistics isn't just about finding patterns, but about navigating the exponential growth of data and the increasing complexity of its sources. Consider the critical need for accurate disease modeling during a global health crisis. Without robust statistical frameworks, public health decisions, from resource allocation to intervention strategies, could be based on incomplete or misleading insights, leading to dire consequences. This was the reality faced in early 2020, where the rapid spread of novel pathogens demanded immediate, data-driven responses, yet the analytical tools and personnel were often playing catch-up. The tension lies in translating vast, often messy, real-world observations into actionable intelligence under extreme time pressure. The traditional academic path in statistics, while foundational, often grappled with the direct applicability of its theoretical underpinnings to these fast-evolving, data-intensive problems. Many graduates emerge with a strong grasp of probability theory, statistical inference, and regression analysis, but perhaps less exposure to the computational demands and the scale of data encountered in industry. The gap was evident. Understanding the theory of hypothesis testing is one thing. Performing it on petabytes of streaming sensor data or millions of customer transactions in near real time is quite another. This divergence created a demand for individuals who could bridge the theoretical rigor of academia with the practical, scalable demands of industry. The rise of data science emerged as a direct response. Data science, in essence, is a multidisciplinary field that employs scientific methods, processes, algorithms, and systems to extract knowledge and insights from structured and unstructured data. It leverages expertise from statistics, computer science, and domain knowledge to analyze phenomena with data. Within the broad umbrella of data science, biostatistics carved out a crucial niche, particularly in fields like medicine, public health, and biology. Biostatisticians apply statistical principles to the design of experiments, data collection, analysis, and interpretation in biological and health-related research. Their work is vital for clinical trials, epidemiological studies, and genetic research, ensuring that findings are statistically sound and can lead to improved health outcomes. The specific challenges here involve dealing with biological variability, complex experimental designs, and the ethical considerations inherent in health-related data. However, the sheer volume and variety of data, coupled with the need for sophisticated predictive and prescriptive analytics, push the boundaries of traditional statistical methods. Techniques that were effective for analyzing hundreds or thousands of data points struggled when faced with millions or billions. This necessitated the development and adoption of more computationally intensive methods and a deeper understanding of algorithms capable of handling big data. The transition from academia to data science for statisticians often involved acquiring new computational skills. Proficiency in programming languages like Python and R became essential, moving beyond statistical software packages. Understanding database management, including SQL, and distributed computing frameworks like Spark became increasingly important for handling large datasets that could not fit into the memory of a single machine. This evolution wasn't always seamless. Statisticians accustomed to the controlled environment of academic research sometimes found the messiness and ambiguity of real-world data challenging. Cleaning, transforming, and preparing data often consumed a significant portion of a data scientist's time, a stark contrast to the often pre-processed datasets used in textbooks. The principle of garbage in, garbage out became a daily operational reality. Furthermore, the rapid advancements in machine learning presented both opportunities and challenges. While many machine learning algorithms have strong statistical foundations, their practical implementation and interpretation often required a different mindset. Concepts like regularization, cross-validation, and hyperparameter tuning became standard tools, extending the traditional statistical modeling toolkit. Biostatistics, while benefiting from these advancements, also maintained its unique focus. The core objective remained the rigorous analysis of biological and health data. For instance, analyzing the efficacy of a new drug involves not just statistical significance but also clinical significance, requiring close collaboration with medical experts. The development of advanced statistical models for genomics and proteomics, for example, demands a deep understanding of both the statistical methodology and the underlying biological processes. The Beyond in a Statistics career path encompasses several emergent and expanding areas. One significant domain is causal inference, which moves beyond correlation to establish cause and effect relationships. This is critical in policymaking, A/B testing, and understanding intervention effects, where simply observing an association is insufficient. Developing valid methods to infer causality from observational data remains an active and crucial area of research. Another burgeoning field is the application of statistics in artificial intelligence and machine learning at a fundamental level. This includes research into the theoretical underpinnings of deep learning, developing more robust and interpretable models, and addressing issues of fairness, accountability, and transparency in AI systems. Statisticians are uniquely positioned to contribute to the mathematical and probabilistic foundations of these technologies. The increasing availability of complex, high-dimensional data from sources like sensors, social media, and scientific instruments has also fueled the need for advanced statistical modeling. Think of time series analysis for financial markets, spatial statistics for environmental monitoring, or network analysis for understanding social interactions. Each of these requires specialized statistical techniques and computational approaches. The integration of statistical expertise with domain knowledge has become paramount. A statistician working in finance needs to understand financial markets, while one in marketing must grasp consumer behavior. This interdisciplinary collaboration ensures that statistical models are not only mathematically sound but also relevant and actionable within their specific context. The career trajectory in statistics is thus characterized by continuous learning and adaptation. From the theoretical rigor of academia to the applied, computationally driven world of data science and the specialized domains of biostatistics and beyond, the core skill set evolves, but the fundamental principles of data analysis, inference, and interpretation remain central. The ability to translate complex data into clear, evidence-based conclusions is more valuable than ever. The future of statistics involves further specialization and the development of more sophisticated tools for handling increasingly complex data challenges. Areas like uncertainty quantification, robust statistics, and interpretable AI will continue to grow in importance. The statistician's role is not diminishing, rather, it is expanding and deepening, becoming integral to nearly every scientific and technological endeavor. Ultimately, the journey from academic statistics to a data science, biostatistics, or specialized role is a testament to the field's adaptability and enduring relevance. It's a path that demands a blend of theoretical mastery, computational proficiency, and a commitment to extracting meaningful insights from the ever-expanding universe of data, ensuring that decisions are informed, robust, and impactful.